Hello and welcome to this GA webinar. My name is Robert Fürst, Frankfurt, Germany, and I'm your host for this session. I'm very happy that Professor Thomas Schmidt from the Institute of Pharmaceutical Biology and Phytochemistry, University of Münster, also here in Germany, agreed to give this lecture. It deals with a very fascinating topic, screening virtual and physical natural product libraries to identify bioactive hits and leads. Let me just briefly introduce Professor Schmidt to you. He studied pharmacy and after obtaining his PhD degree in pharmaceutical biology in Münster at the at Düsseldorf, University of Düsseldorf, he went as a postdoctoral fellow to the Louisiana State University in Baton Rouge in the United States. In 1999, he finished his habilitation. The topic was the structure and activity of certain cis-quaterpine lactones in pharmaceutical biology in Düsseldorf, and then after working as an assistant and extraordinary professor in Düsseldorf, he went in 2005 to the University of Münster. He was actually awarded with several prizes. Just to name one famous, in 2000 Professor Schmidt received the prestigious Egon Stahl Award of the GA. Moreover, since May 2016, you might have noticed this, he's editor-in-chief for the section Natural Products of the journal Molecules. Okay, that's all. Let's get started. Professor Schmidt, we are very much looking forward to your presentation.
Yes, thank you very much, Professor Fürst, for this kind introduction, and also thanks to GA for giving me the opportunity to speak here. And of course, it's kind of unusual to me because it's the first time I'm giving a webinar, so that's giving a lecture without seeing the audience. Nevertheless, good afternoon to everybody, everywhere, wherever you are watching. And I'm happy to share with you this webinar on a topic which becomes more and more important nowadays in natural product research groups. The search for bioactive natural products as starting points in drug discovery and development has, of course, a very long tradition, and it is still a very important approach in our modern times, as you are probably all aware. Using state-of-the-art computational methods is becoming increasingly important in this field, and it has for a long time largely been governed by the well-known bioassay guided isolation approach in our field. But as I said, computational methods are getting more and more important. And therefore, in this webinar, I will show you some of the methods that we use to screen or mine libraries of natural products in order to find new active molecules. So I should start the first slide, actually, because I'm speaking of the topic of my webinar. Well, one part of this will be directed towards analyzing the information content of virtual libraries of natural compound structures using computational tools in order to explain the bioactivity of the represented compounds in these libraries in terms of structure and to successfully predict the activity of yet untested compounds. These can then be retrieved from their biological sources or obtained in another way and tested. And if we're lucky and have done everything correct, then of course we may end up with new biologically active chemical entities. In the second part of the talk, I will show you that using very similar computational tools, we can also analyze the content of what I like to call physical natural product libraries. That means crude extracts or their fractions or mixtures of natural products of any kind, and how we can pinpoint the compounds in such complex mixtures that are responsible for their bioactivity. And for that we can use very similar computational tools. Both of these approaches are, of course, methodologies complementary to the classical activity-guided fractionation approach. Now, choosing the metaphor of a library that is used for collections of chemical structures or other chemical entities, because just like a real library, they contain a huge amount of information, or they may contain a huge amount of information. And now imagine you come into a library you don't know, you look for a particular piece of information, and you don't know where to start the search. somewhere here in these halls, there is the information hidden which you are looking for. And now, of course, it may be helpful if you have somebody to show you the way. A librarian, for instance, an experienced librarian, who might guide you to this shelf and might show you the book that you're looking for, and he might even show you the page you are looking for with a piece of information you're looking for instance, this particular plant, and this particular sentence telling you that this plant probably contains compounds that can be used against malaria, because this is a page on a plant actually from Dioscorides' book, famous book, showing you that this has been used against cold and fevers that recur after several days. So that might be a piece of information telling you that this plant has been used against malaria. Now, in this lecture, we will not be looking through a library of books, of course, and our librarian will not be a real librarian, but mathematical, statistical methods of data analysis. We will not look for a sentence, of course, but we will search for a piece of information showing us the compounds that have a desired biological activity. A natural product library, a virtual natural product library, in our case with containing the structures of natural products, is in fact nothing but a big table containing as objects in the rows the structures of the compounds we want to analyze. The columns of the table, they contain information about these compounds, features, properties, for instance, the biological activity in numbers, and other properties characterizing each of these molecules. Now, such tables can have an immense size, and such libraries are sometimes many, many thousand compounds high and can also be many, many thousand columns wide, because many things can be expressed in numbers that relate to a chemical structure. If we analyze them in a proper way, we can find in them two things: the structural reasons why a particular compound has a desired biological effect or bioactivity, and as a consequence of that, we can also find compounds in the same library or maybe in another library that have similar properties but have not been tested so far, and that might also be active. And from the proper analysis of the data in this library we use for training, we may make predictions for untested compounds, retrieve these compounds, test them, and hopefully have a good hit rate, as we say. On the other hand, actually there are different approaches to screen such virtual natural product libraries. One approach is called structure-based virtual screening, which is then applied actually in cases where we know exactly the structure of the biological target, the three-dimensional structure of a protein, for instance. And then in such cases, a library, ligand sources here in the slide, can be investigated by virtual screening, looking at the protein structure using docking, for instance. And this is obviously a very straightforward way to fit the compounds of a library into the active center of an enzyme we want to block, for instance. This is the more straightforward way, even though it's computationally demanding, but we will not concentrate on this approach in our present webinar here, but we will deal with a more difficult case actually, which happens quite often, or even in more cases. And that is the case where we do not exactly know the biological target. Sometimes we do not even know the exact mechanism of action of our active molecules we want to investigate. And that is called ligand-based virtual screening. In this approach, we have to confine to an analysis of the structural properties of the molecules we have and their activity data, and to construct so-called QSAR models, quantitative structure activity relationship models, which are mathematical models that describe and explain why some molecules are more active than others and some molecules are less active. And if this mathematical model we have created at the end is a statistically sound model, a reasonable model, then we can use it for activity predictions of other molecules, of huge databases, and just filter out those molecules that may be interesting to test. So that method is actually the one that I will concentrate on today with respect to virtual natural product libraries. A physical natural product library, as I indicated before, in my eyes, or in this definition of our talk today, is simply a mixture, a physical mixture, physically existent in the lab of natural products. That can be a whole plant, a plant powder, for instance, or more frequently an extract, for instance. And of course, the constituents of this extract can also be treated as objects in a library. We'll see that on the next slide here, where we have, for instance, the chromatographical profiles, the HPLC profiles of a set of extracts. You see that there are some similarities between these chromatograms, but on the whole it's kind of difficult to see exactly at one side which of the peaks here are the same in every extract and which are not. But of course, such a series of chromatograms already has kind of resemblance to a table. And of course, we can transform it into a very similar data table as we've seen before. In this case, the objects are our samples, the extracts or fractions or whatever we have analyzed here and want to compare and to analyze with statistical methods. And of course, the columns, again, contain the features of each of the extracts. In that case, it is information about the constituents, chromatographical, retention times, and for instance, mass signals, mass spectral information. So we end up with a very similar table that can be analyzed statistically, mathematically, in a very similar way as a pure compound library. So it's important that you keep in mind we are dealing actually with data, and these data have a very similar format in both cases. Now, when we want to analyze the information content of such a library, be it a compound library or be it an extract library, the entries in the library that have similar features are also supposed to have similar properties. Very simple thing, very straightforward to assume. And a property of interest can be considered as a function of particular features. Not all the features we have in this table. This table can be very huge, as I said, many hundred columns wide and many hundred or many thousand objects deep. The property of interest is considered a function of particular features. That means we have to find those features which are of particular relevance to the function and to the property that we are looking for. Now, how can we find these relevant features? Of course, it would be very useful to compare these objects with statistical methods for similarity or dissimilarity and to try to relate the similar features to the similar bioactivity. High activity should have a correlation, a direct correlation to similar features that probably then are related to this high activity. Now, then the next question arises, what exactly means similarity or dissimilarity? And in that point of this lecture, it may be a good idea to ask you the question, which is shown here. Which two of the three objects do you consider most similar to each other? You see three objects here, A, B, and C. And then, of course, it may immediately arise to you that you can compare them for different features, and it always depends on your point of view. If you're a biometrician, for instance, you would compare the volume as one feature and the length over width ratio, for instance, as a second feature, and you would create something called a feature space, a very simple feature space. In this case, you have a two-dimensional space, actually, and in that feature space, you would of course see that A and B are much more similar to each other than C. C is much smaller, even though on the photo it appears a little bit magnified. If you're a biochemist, same thing. You would maybe compare the oxygen consumption and the content of DNA and protein or whatever biological molecules, and you would find B and C are much more similar to each other, and A, of course, is completely different. As an immunologist, you would maybe measure the content of cytokines and kind of a response, immune response, and then you would find A and C are more similar to each other because C is a immune-depleted mouse, and B, of course, has a high content of immunologically relevant molecules. So it depends on the standpoint, very simple assumption. And if we transfer this, for instance, to these three chemicals here, you see that molecules A and B at first sight, if you just look at them with the eyes of a chemist, an organic chemist, they are very, very similar to each other. You even have to search for the difference. You see that B has a saturated isopropyl group where A has an isopropyl substituent, but the rest of the molecules is virtually identical, and C looks very much different. As a chemist, of course, it would be clear A and B are similar in this feature space. As a biologist, you would maybe compare the biosynthetic pathway and the producing organism as features, and in your feature space, again, A and B are almost identical and C is different. But as a pharmacologist, you would maybe notice that A and C are very toxic molecules. I have here the log D, the negative logarithm of the LD50 against mouse, and both of them, A and C. So these two are very similar in that respect, having an LD50 about 1 milligram per kilogram, and B is quite untoxic. And the binding affinity towards a particular receptor protein, GABA-coupled chloride channels, in A and C is also very similar. And B doesn't bind to this receptor. This is actually the reason for the toxicity of A and C. So how can these two be so similar that they have the same mechanism of action as is actually known for these two molecules, picrotoxinine and anisatine, and what can be the reason for that, even though they look quite different? Well, looking at them with the eyes of a medicinal chemist, you would notice that A and C have particular features in common which B does not have, or in which B differs gravely, because the isopropyl group here sticks actually out of the molecular plane where A and C have a relatively flat hydrophobic surface element. And that is one part of the reason why actually you would notice as a medicinal chemist doing some binding studies and compare the structures to each other, you would notice that A and C are similar in particular features, not only this region I mentioned, but also some hydrogen bond accepting features that make them actually able to bind to the same receptor in the same way and do exactly the same job. In that case, high toxicity causing epileptiform convulsions, and B is inactive. So it depends really entirely on the standpoint or on the point of view. And we have to find ways to filter out the relevant features from such databases. Now, speaking about properties and features, what is a property, what is a feature in terms of my lecture today? Actually, a property, the dependent property, we call it a Y value later on, of an object, of object A, can be considered a function of one or several other properties, which I would like to call features, like the molecular features, like things like the molecular size, etc. Everything that you can express in numbers. And these features will be termed X values. So this is the simple equation underlying all the things that I'm saying today. The dependent property Y of an object A is a function of its independent features, the properties, that means the features, the X values of this object. The working hypothesis is that the properties and features of different objects are related to each other in the same manner. That is some very important prerequisite for any such study. We must assume that they do the same thing. They have the same mechanism of action. And thus objects with similar features X will also be similar in property Y. So S stands for similarity, a proportionality between the similarities in the X and Y properties or features. Now, this principle implying a causal relationship between properties and features can be used to investigate causal relationships by applying statistics. And what is similar? I've asked that before. Which features are responsible really for the similarity of a particular property? That is what we want to find out. The properties and features for that, or to this end, need to be expressed in numerical form. Of course, we want to use a computer, so we need a numerical expression for each feature and for each property. And then we can imagine our table. The n features of the m objects represent an n-dimensional feature space. I showed you this simple feature space with 2 dimensions and 3 objects. In this case, we will have an n-dimensional feature space for our m objects, and the feature values of each object then represent the coordinates in that feature space. So that means we have to imagine we navigate in a multi-dimensional space and have to find the right dimensions actually, which are important. Similarity and dissimilarity between the objects are determined by their positions in this space. The closer 2 objects are, the more similar they are. Of course, that is kind of logical, and we can apply statistical methods to identify correlations many times, and most of the methods we apply are linear correlation methods between the features and the target property. And that means to navigate, as I said, in this multi-dimensional space to find the relevant dimensions. And the other dimensions we can ignore. It's just important to know which dimensions are responsible for our property of interest. So what we actually try to do is to simplify this highly complex feature space with many features in this huge table, and just to filter out the few features that we want to know, or that we want to that we are interested because they are responsible for our biological effect. And it is very straightforward that it becomes easier to navigate in such a feature space the more objects we have to compare, and the higher the variance of these objects will be with respect to the property of interest, this target property. Now, let's come to mining virtual natural product libraries, compound libraries to identify bioactive hits and leads. Where in this library are the important features explaining our activity? So for that end, as I said, we will concentrate on the properties of the molecules that we have already tested and use the information later on for predictions. Now, to mine such a virtual compound library, actually we need numerical values. I've said that before. The numerical expressions for features of the molecules are usually called descriptors because they describe some particular property of the structure or of the compound in numbers. Descriptors can, as you can imagine, be extremely manifold. A descriptor can be any feature of an object that can be expressed in numbers. Methods exploring feature space of descriptors of molecules are called quantitative structure property relationships, QSPR, and a particular subcase of that is QSAR. The target property in that case is a biological effect, activity, and then we speak of QSAR or quantitative structure activity relationships. What we try to do actually is to analyze the structures here and also analyze, of course, the property, in this case here a biological activity, for instance, determine the activity data, get the structural descriptors, the structural features as descriptors, and find this mathematical correlation between descriptors and activity. And then we get hopefully a useful QSAR model, which has 2 important properties itself. because if it's useful, it can explain the activity in terms of structure. It can tell us, okay, this part of these molecules here is particularly important. And at the same time, and that is sometimes even more important, is that a useful QSAR model must be able to predict the activity of untested analogs. Otherwise, it will be purely explanatory, which is also nice, but of course we want to extrapolate this model to untested compounds to find new active molecules. Now, what can be descriptors? Descriptors can be, as I said, many things. We can divide them, or we can put them into classes depending a little bit on their complexity. There are first very simple 1D descriptors. That means descriptors or features that are related to the elemental formula. Very simple thing, one-dimensional formula. And we have, of course, the possibility to calculate from it the molecular mass, count the atoms. We can say, okay, this is a descriptor. This molecule has 15 carbon atoms. Other molecules in the series could have only 13 or whatever. So very simple descriptors derived from the elemental formula are 1D descriptors. Second class would be 2D descriptors, which are derived from the molecular graph, from the 2D structure. So they are features that can be related to the atom types or to the bond orders or connectivity within the molecule, the topology, as we say. And sometimes you also use special types of 2D descriptors, which are very simple to obtain, which are indicator variables that assume the value of 1 if a particular feature or structural group is present, like for instance this oxygen in this position, and that would assume the value of 0 if we do not have an oxygen in this position in another molecule. So it's something like that. Some values like that or features like that can be expressed in simple type 1,0 descriptors. So anyway, for that we need 2D information of the molecular graph. And then, of course, we have a huge array of 3D descriptors derived from the three-dimensional molecular structure. These are features related to anything that is a consequence of the three-dimensional conformation of our molecules, like the surface area or the volume of the molecule, the shape of the molecule, internal energies of the molecules, descriptors that are related to electron density or distribution, like this electrostatic map here on the right side, or this electron distribution or charge distribution on the molecular surface, etc. So any numerical value that I can derive from such three-dimensional models are 3D descriptors. There are even more complex types that are computed by using so-called molecular interaction fields, which can assume or can be very complex to calculate. Anyway, anything that you can imagine, that you can express in numbers, can be a descriptor. Probably the most comprehensive collection of molecular descriptors, if you ever want to look at a particular descriptor and also understand a little bit how it is calculated and its meaning, you can find in this very famous book by Todeschini and Consonni here, and the software corresponding actually to the work of these two colleagues here, the software Dragon, that has been on the market for a long time, is also available, the address shown here, and this can calculate about 5,000 different descriptors for a set of molecules in almost no time, very quick calculation in most cases. So that can be helpful. But usually, or very often, 5,000 descriptors is a little bit much. We don't need so many normally. And most modeling packages, like for instance the molecular operations environment, a package that my group is using, they offer something like a couple of hundred different descriptors to calculate. Now, first thing we need, as I said, is a library table or a so-called study table containing the molecules. We've seen that before. The target property, our dependent variable, the Y data in one column, usually the first or the last column of this table. And then the features, the N features, descriptors, as many as you want, as little as possible, hopefully, maybe you don't, or as few as possible, I mean, you don't want to overload your table with information. And then, of course, we have our study table and we can start thinking about constructing a QSAR model. Maybe a few words about the selection of useful features, that means descriptors, might be useful in this moment, or at this moment, because that defines actually our starting feature space. The descriptors, as I said before, represent the coordinates of the objects in this n-dimensional feature space. And the initial definition of this feature space is of crucial importance. If we define it too large, then it can be very difficult to find the few relevant variables in this huge assembly of variables. Now, actually, there are some rules which are also a little bit more explained in a little bit more detail in an appendix to this presentation. There are some extra slides which I cannot show here for time restrictions, but one thing to keep in mind is that the x variables and also the y variable, the target value or the dependent variable, should be as close as possible to a normal distribution in this table. If there is a strong deviation from a normal distribution for our data set, then this can lead to distortions in the models that we create, and this is never a very good starting point. So the target variable should optimally be used then in molar dimension. We are supposed to compare molecule by molecule with each other and not mass units with mass units, so that's a very important thing. And they are to be used in logarithmic form. Why that is so, you will see in a moment. And since descriptors have often very different dimensions in such cases, like for instance the molecular volume in cubic angstroms and the molecular surface in square angstroms and the molecular dipole moments, whatever, in debris, for instance, they have different dimensions, and that's why they should all be scaled to unit variance. That means dividing each column by its mean value, so that they all become or they all receive an equal weight in our mathematical operations we want to start. And one very important thing is also that the degree of cross-correlation between the variables should be as low as possible. So we should not have so many redundant variables in our table. That means not so many variables which are correlated among each other, because actually then we have redundancy, many columns, for instance, that contain virtually the same information. So it can, in such cases, be better to consider only one of these pairwise correlated variables, descriptors. Then the model building process as itself is kind of a cyclic process or an iterative process. We need a method to fit our data. That means to find correlations between particular x variables and the target variable. We need more methods to validate the model, of course, and then, of course, we also need methods that help us to select the relevant descriptors. And we repeat such a cycle by finding out whether the model we found so far is of sufficient quality. If this is not the case, then we have to think about other descriptors. And if we find out at the end, okay, yes, it's okay, then we can be happy, we can publish something. Especially we can predict new molecules and find maybe something even nicer to publish a little bit later. Now, enough theory, I think. This was a lot of theory actually, and I will now go with you or try with you to show you how to construct a very simple QSAR model with a very simple data set. Actually, the methods we have available for data fitting, the most important, the central part in this method, are usually, or in most cases, linear regression methods. We can use multiple or single linear regression. Usually we need more than one variable, so we have to use multiple linear regression. The second method is the principal component regression, and the third one is the partial least squares regression, which are particularly suitable when we have really huge X matrices with many, many more columns than we have rows in our table. For a simple case like the one that I will start to introduce you with, we can use multiple linear regression. This is suitable actually to analyze small X matrices, where the number of variables is not much larger than 3 times the number of objects, something like that. So, and then of course, just to complete this slide, there are other methods which do not rely on linear correlations, neural network methods, for instance, decision tree methods, other methods that are a little bit more complex, but in many cases, in a problem like ours, to construct a Q-sum method, we can really rely on linear regression methods. And that's still the basic method, or these are still the basic methods used in most such studies. Now, as I said, we want to start a little experiment together and make a little, construct a little Q-sum model. And this is based on literature data for an energetic activity of some capsaicin derivatives. The basic structure is shown here. The R here, as a if this R is a proton, then we have capsaicin, the native natural product. And well, quite a long time ago, some authors have compared the activity of singly substituted, in this para position, substituted capsaicin derivatives. Their potency, actually, this was an in vitro model which can be extrapolated to energetic activity, and the EC50 values, that was is the how do you say, the concentration EC50 that abolishes 50% of this measured in vitro effect is shown here in micromolar, and in the right column we have the negative decadic logarithm of that concentration if it is expressed in molar concentration. So the PEC50. This example simply is a very simple statistical example. It was just the statistics were performed with Microsoft Excel, where you can do multiple linear regression, and the descriptors that I use were calculated with a Mo package. And this is the study table, a very simple, very small study table. I only chose for you 11 or 12 descriptors here. As I said before, we have our table with the biological data. In this case, I left both columns here for you as a starting point, and then we have the descriptor values. And these descriptors are just molecular properties which can be calculated very easily from the molecular structures. Now, the first thing we want to know is actually the degree of correlation between each of our X variables, our independent variables, and the dependent variable, the biological activity. And to that end, it's always good to take a look at the so-called correlation matrix, which contains, as a square, symmetric matrix. That's why only half of the values are shown here. The other half is not shown. It would be the same values actually, which contains the degree of correlation, or the coefficient of determination actually for each pair of variables. And of course, what is interesting in the first moment is the degree of correlation of these variables with our biological activity. And as you can see in these first two columns, there is not particularly high degree of correlation between many of these variables and our two columns of biological activity, but the PEC50 here is very highly, very strongly correlated with two variables here, log P OW, the partition coefficient between octanol and water, calculated value in this case, not an experimentally determined one, but it's not so important, has a highest degree of correlation with our PEC50 value here. And then there is another descriptor, which I called variable X here, which has also a degree of correlation more than 0.9. So that is also a very strong single correlation of this variable with the biological activity. And then, of course, you can see that some of our X variables are also strongly correlated with each other. That is a case which I mentioned a little bit earlier, which is actually something we normally want to avoid. We do not want so many cross-correlated variables in our data matrix. But for the time being, for this moment here, I left these in the table, in the data set, and we will just take a look what happens when we plot the activity data and the most highly correlated variable here, log p, with versus each other and generate a correlation plot. And do the same, sorry, I go back again, and do the same for the non-logarithmic activity data, which are in the first column here, and take a look how these data correlate with each other. In the left diagram, you see the correlation of log p with the PEC50, the logarithmic value, and in the right one, you see the correlation of that descriptor with the non-logarithmic. I'm sorry, there is an error here. There should not be a p in this label. So these are the non-logarithmic raw data, and you see that the degree of correlation with the logarithmic data is a lot higher than in case of the non-logarithmic data. Now you may say this can be a coincidence, but in fact this is a common observation actually, or a common observation that the logarithmic data have normally a much higher degree of correlation with relevant variables than the non-logarithmic data in such cases, and that has to do with the fact that we are looking actually at linear free energy relationships, which are defined a little bit more detailed on an extra slide in the appendix, where the physical background of this is also explained again. Would take a little bit longer now at this point to explain this, but we take it for granted, and this example shows it quite nicely, that the logarithmic data are actually the ones that we use for our biological activity data, or for any other property that we want to correlate with molecular features in other QSPR models. Now what we want to do is we want to obtain a linear correlation or linear regression, perform a linear regression, multiple linear regression, or single linear regression, with the aim of finding an equation that has coefficients for each of the x variables that are relevant, which yield the best possible correlation of the calculated and experimental y data. So the simplest form would be one variable is mostly responsible for the variance in our target values, so then we can do with a single linear equation, or in most cases we need more than one variable to obtain a satisfactory fit of our data, and then we have to use multiple linear regression. Two things on this slide are very important. I think I mentioned it before. MLR works best if the X data show no cross-correlation, so the variables that come into our final equation should have as low as possible degree of cross-correlation with each other. And at least as important, the second point here, MLR works only when the number of variables we use for such a model is much smaller than the number of objects, the number of compounds. That is something we always have to keep in mind, and we will also see what can happen if we use more variables than useful. Now, let's look at this plot again, our log p value here, the PEC50 data plotted against log p, and of course we can fit a linear trend line through this data and also find the equation for that linear trend line, which is shown here, and also find the coefficient of determination, the R-square value, which is quite fairly high in this case, which means simply that 87.5% of the variance in our biological data are explained by the variance in the variable here, in the log p data that we've used. So that is already quite a good fit for one particular variable. So a large part of this biological activity differences are actually related to differences in lipophilicity, in the log p value variation. But what about the other 13%? We'll talk about that a little bit later. Maybe we can explain even more of this variance if we add another variable to our model. At this moment, also, I want to explain to you that this simple trendline equation here can also be used, or can be used in another form, in the form of a so-called QSAR equation, because we can substitute it, and then we will find that our PEC50 equals coefficient 0.85 so-and-so multiplied by log P plus the intercept value here actually gives us the regression equation for that very simple QSAR model with one variable, and that is simply a different plot here showing you the calculated values, calculated with this equation, versus the experimental values. And that is usually the representation we choose when we want to depict or to describe a QSAR model. Calculated versus the experimental data are plotted. The picture is almost the same, but both axes now have the same dimension, of course. And what we can see in this equation is the coefficient that is responsible, or that has to be used to multiply our log P value to obtain the best fit of our data with this equation. Now, as I asked before, we have 87% of our variance already explained, but how about the remaining 13%? Can we use another variable maybe to explain more of our variance? Now, in this case, if we want to try this, then we can keep the log P in our equation and calculate or to generate a bivariate linear equation, adding a second variable, and we can simply try each of the other variables in our table, generate such a bivariate linear equation, and see how the R square, the degree of correlation or the coefficient of determination, changes. And as you see, it increases in particular cases quite strongly, while in most other cases here it remains more or less the same, or there's only a small increase. We have a second value here, the so-called adjusted R square, which is even more important. The adjusted R square is an R square adjusted by the degrees of freedom in this equation. That means it will only increase if this new variable gives a significant, statistically significant contribution to the new equation, which makes it better than the one we had before. And you can see that this adjusted R square is also increased over the first equation we had, where it was only 0.85. Now it's increased here in case of variable x, and also in case of this descriptor called ASA plus here, which I've also shown in red. In all other cases, it decreases. And once you see that your adjusted R square decreases, this means adding this variable, one of these variables here, would be completely useful. Same, we conduct a t-test. The p-value, the confidence level value actually here, is relatively low in case of the two variables shown in red, and it is relatively large, very large even in the other cases, indicating that none of these variables would do any significant statistical good to a bivariate linear equation. And finally, the f value from the so-called f-test or Fisher test, this f value in a similar way has not decreased strongly, especially or exactly if we compare it with the first single equation here. It's still in the same range in both cases here, but it has more or less dramatically decreased for the other variables. So that means also the same, these two variables might be used as second variable in such linear relationship models, whereas all the others here are completely useless. So we can concentrate on the two variables which are shown in red. Now let's take a look again at our original picture. This is just the univariate equation we've had before, the PEC50 plotted against log P value again. And we might notice in this case that the linear trend line we've created previously has a pretty good fit with a data point, but that a polynomial trend line containing an additional term, the square of the log P value as a second variable, would create a much better fit. You can see that this trend line here has a much higher coefficient of determination than the linear one. So this is a polynomial trend line containing log P square and log P as variables. And then, of course, you get a parabolic trend line, which is much better fitted to these points. And I'm showing you this because that is something, or that's a phenomenon which can occur frequently when lipophilicity or hydrophobicity is relevant as a descriptor to a CUSA model, which is not always the case, but relatively often occurs. And there is a very simple explanation for that. Looking at this plot again and extrapolating it, this parabola here would mean, or would indicate that with log P values increasing over a maximum, the bioactivity is decreasing again. It's becoming less active again. What might be behind this? So something shown here, something like that. We obtain a linear relationship in this region, but if we would increase the log P value for compounds which are even more hydrophobic, the activity would go down again. And this can be explained simply because log P, of course, has to do with a penetration, or has an influence on the penetration of biological membranes and barriers. And of course, if a compound gets too lipophilic or too hydrophobic, then it will make it very easily into the membrane, but it won't come out again on the inside. So it cannot penetrate into a cell where it should have its biological activity. So that is the reason why in case of log P dependent bioactivity, we usually get something like this parabolic relationship here. So it might do quite good also to include beside log P itself the square of log P. And now let me come back to our table, and I called this variable x in the beginning, but actually the variable x is nobody else but the square value of log P. So I have already included it in the original table, but for didactic reasons I call it variable x in the beginning. So taking log P and its square would increase the correlation coefficient here to 0.939, and it would also be a significant increase in the quality of this bivariate model over the univariate model. Now, the energetic activity plotted as a function of these two variables, you see here, this is the equation behind it. Actually, you see that the linear fit has been gotten much better, since, of course, log P square is now included in the linear equation. So we don't need a parabolic trend line anymore. And the CUSA equation in that case becomes or receive the form that is shown here. So that would be an even much better model than with only one variable. Now you've seen that there is yet another variable here, a descriptor called ASA plus, which also promises to give an increase of statistical quality of correlation. So it may also be meaningful to the explanation of our biological data. And we've done that before. We've seen that the adjusted R square in both cases with the log P square value and also the ASA plus value increases over the first model. The P values are okay. The F value does not decrease very significantly. So all of these things indicate to us that both variables here might be useful. So we could get the idea maybe to try a trivariate model, a model with 3 variables, and include all of them. So this is just a slide showing you both models separately, both of the bivariate models. Here's the one with log p and log p square. Very good linear relationship. And here is the one with log p and the ASA plus variable, another descriptor related to the charge distribution on the molecular surface. And also we have a very, very good, even a little bit better coefficient of determination here. So we might get the idea, as I said before, to use a model with 3 variables. What would happen then? We would have to look at our statistical parameters. Here is once more shown a table for the bivariate model with only log p and log p square. You see the p-values are bearable, they are not so bad. The f-value, as I showed before, is in the same range as the original one for the univariate equation, and the adjusted r square has increased. So that is a statistically useful model. Now this is the table, the same ANOVA statistical analysis table we would get for a trivariate model. Could try to include, as I said before, to include all 3 variables in this model. And what you see at the first sight is that the adjusted r square has decreased. It is worse than before, even though the normal r square, the not unadjusted r square, has further increased here. But the f-value has gone down to almost about half its value, and all 3 p-values are completely insignificant, indicate that none of these variables is significant any longer. So that shows us this model is not statistically useful. We cannot use this model for anything, and that's why we have, in this case, actually reached the maximum of what is possible with only 7 compounds, a model with 2 variables, and a pretty good fit, actually. And this can be either the one with log p and its square value, or the one with log p and the ASA plus variable. We cannot decide actually which one. So in this case, that would be the point to stop and say, okay, we have 2 models, and probably log p and its square are very important, and it may also be possible that this value related to the positive charge on the molecular surface area is also of relevance to the biological activity. We simply cannot go beyond a number of variables in such a simple MLR model, a multiple linear regression model, where the number of variables is in this region. The rule of thumb is that the number of objects should be larger than 3 times the number of variables. So 3 times 2 variables would be 6, and we have 7 objects. This is still useful, but anything else, 3 variables, would be just too much and statistically useless. This is something which is quite often overlooked. Just to show you one example. I don't mention names, I know, but I don't tell you at which conference this was taken. This photo was taken by one of my PhD students, Freddie Bernal, and he sent it to me and writing, look at this, professor, I found this CUSA model here. And there is a CUSA model described with a correlation coefficient or a degree of correlation of 1, r square equals 1. And you can be sure, without looking at any other details in this study, that this is actually a result of overfitting the model, using too many variables, because using one more variable will always increase your r square. But these authors here probably have not looked at the adjusted r square, at the p-values of their descriptors, or at the f-value. Now, let's not remain here so long, but this is how a CUSA model should never look at the end. Now, I've shown you a very simple method to select variables. That was the first point here on this slide, called forward selection. We choose a variable that has the highest degree on its own of correlation with our target value, and then from there on we successively try to add further variables and see if the statistical quality increases. That is called forward selection. We can also use a different approach, using several variables and eliminating useful ones that would be called backward elimination. And we can also use, computers can use combinations of that, adding and subtracting variables and optimizing a model. So these would be methods that can also, in case of small data sets, be done by hand actually, and that is why I chose such a simple method also to demonstrate it. There are more complex automatized methods where you can go and drink coffee and let your computer select the variables for you. And one of these methods is called, or one of these methods actually is based on genetic algorithms. Using a genetic algorithm on such a big data set, a big set of variables, and let the computer use the principle of evolution, of genetic evolution actually, to select the best variables. Now, how can you imagine that? How would this work? There are some other methods mentioned here which I will not go into detail about, because I will show you an example where a genetic algorithm has been used for that purpose. A genetic algorithm actually mimics somehow the principle of evolution. That means we do not start with one particular descriptor or one equation and try to optimize it, but we have to work on a population of models. So the computer generates randomly a population of QSAR equations, for instance with a fixed number of variables, or also with a variable number is possible, just a population of say 100 MLR models in which the variables from our data table are randomly simply included in these equations. For instance, 5 of them in a pentavariate linear equation. Now, actually, the descriptors are used as genes of each individual equation. We have individual equations which are individuals in this population of models. The whole population undergoes evaluation of the fitness. For instance, the adjusted R-square is used as a fitness criterion. The ones with the highest adjusted R-square are ranked most highly. They are the fittest. And the ones with the poorest adjusted R-square would be the poorest performers in this family, in this population. And then from there on, we apply the principles of biology, selection, survival of the fittest. We only let a fraction per certain predefined fraction of these models survive, and replace those that are really unfit by new combinations. We simply use the models that have better performance, and we exchange some of the descriptors, genes, actually for others. We take other descriptors instead, and also we can mimic, or we can model the crossing over by simply crossing or simply exchanging between the models some of these descriptors, mutation and crossover. And then the models are fitted again with a regression method and evaluated again. And those that have an increased and an improved adjusted R-square, of course, they are fit, they survive, and some of the poor, the particular fraction that we have defined previously, will die out, they will go extinct. And in this manner, we conduct hundreds and hundreds of cycles and thereby optimize our model population, our family of models. And at each step we ask, is a particular predefined termination criterion reached? That would be, for instance, adjusted R-square equals 0.9, for instance, or 0.85 or whatever. Is it reached? If not, then we continue. If it has been reached, yes, we have the final optimized population of models, all models with a high degree of fitness, usually. If our descriptor table contains relevant variables, we will, with almost deadly certainty, find a family of models with all relevant variables in these equations. Sometimes it doesn't work. That means the descriptors we've looked at are simply not descriptive enough for the particular question we are asking. But I want to show you an example from my own work where we have applied this technique. A real example using this genetic algorithm multiple linear regression method, GAMLR. And that is a QSAR for the activity of a set of sesquiterpene lactones against their activity against Trypanosoma brucei rhodesiense, causative agent of the East African form of African trypanosomiasis, of sleeping sickness. Now here you see the structures of these molecules. You can see all of them are structurally related, sesquiterpene lactones, different skeletal types. And in this table, which actually contains also data for other parasites, this first column here shows you the IC50 values against TB rhodesiense in micromolar. And that is only part one of the table. What you may see is that some of these compounds 1 and 2 in particular, have very low IC50 values in the nanomolar range. They are very particularly active molecules, and they were actually the first ones we ever tested against this parasite in 2000, 2001 or something like that. And ever since, we were looking for more active molecules, but as you can see, none of the ones that we tested later were comparably active. This is part 2 of the table. About 70, almost 70 compounds were included in the QSAR study. And as you may imagine, it was, of course, important to understand why some of the compounds are so particularly active. And on the other hand, a QSAR model, as I said before, was supposed to be used for predictions, to find other sesquiterpene lactones with maybe even higher activity. Because, as you may know, when you're a little bit familiar with terpenoids, that about 5,000 or more than 5,000 different sesquiterpene lactone structures are known. And it would be quite tedious and take a long time to test all of them. It would be impossible, of course. But to make a predictive model would be quite a nice option. That was the starting point of this study. So we performed a QSAR study for this activity, creating 3D models of 69 sesquiterpene lactones, optimizing the structures, putting them into a database, calculating a set of 123 molecular descriptors using our software, dividing the molecules into a training set, a set of molecules that is really used to generate the models, do the statistics and generate a model, and a so-called test set, which is a set of molecules we set aside, we take them out of the data set before doing anything to use them later for a so-called test set prediction, when we have a final model to predict the activities and see if the activities are predicted correctly, because that is a very important test for such a model if you want to know whether this model can also be used for compounds which have really not been tested before. Then we performed such a GA-MLR optimization. The variable selection was done by this genetic algorithm, and the fitting method was linear regression, multiple linear regression, so exactly the thing I showed you before. The models then are also validated. Of course, beside p-values and f-values and adjusted r-squares, there are some further methods that are frequently used to validate such statistical linear models. So-called internal cross-validation, leave one out cross-validation, which means simply you create a model, you leave one of the compounds out of the model, make the model under the same conditions again with one compound less, and then take this model and predict the activity for that one particular compound. Then you take this model back, this compound back into the model, take another one out, do the same. And you proceed like that for each compound in your training set. And the predictions you make after leaving out for each of these molecules then are a very good measure for the quality, for the internal predictive quality of this model. And then, of course, at the end, you do the external prediction with this test set, as I mentioned before. So we took about 2/3 of the molecules as the training set, 46 molecules, and 23 were left out as a test set. Found out that the optimal number of descriptors in this model was 5 descriptors in a pentavariate equation. And this was actually the family of models in comparison with models that had 6 variables or 4 variables that gave the best test set predictions. Statistics were pretty good, pretty nice. And what you see on this slide is actually just a summary of these validation methods. You can maybe look at it later. go back to this, scroll back to this slide here. There is one further validation method, which is usually the ultimate test for the quality of your model, which is called the scramble test. I haven't mentioned it so far. And that you usually perform when you think you have a statistically reasonable model at the end. Then you take your data table and you scramble the response data, the biological activity data in this case, randomly, reassign them to the objects in the table, to the compounds, and you perform the model building process in exactly the same way. And of course, with randomly scrambled activity data, you should never get a statistically useful model. Sometimes this can happen in cases where you have chance correlation. Sometimes you have variables that will simply correlate almost with everything, or an assembly of variables that will give good correlations with everything. This can happen. I have had that before. So the scramble test at the end is actually the ultimate test whether you have not been working with something we call chance correlation. And that all of this was performed in case of this data set. And the best equation, the best QSA equation with 5 variables is shown here. We will not go into detail what these variables mean, but we can take a short look at the performance of this model. The calibration data, that means the test set calibration data, are shown as blue diamonds here. You see the correlation is not perfect. R square is about 0.75. Then we have the leave one out cross-validation data. That is for this equation actually what we get when you leave one compound out, predict its activity, and then predict the next one, take the next one out, etc., etc. And then also you get, of course, a degree of correlation or coefficient of determination, which is shown here in red, the red circles. So also these are pretty close to the trend line. They are not perfectly correlated, but after we found that 2 compounds actually here are kind of outliers in this respect. So if you left these out these are the test set predictions. Sorry, I was a little bit confused. So for the test set, we have the red triangles here, and the red triangles actually also show pretty good prediction. So that means the molecules which have never been in the statistical modeling process are also predicted with some confidence, except 2 or 3, which are shown as squares here. If you leave them out, the whole correlation becomes a little bit better. But the whole picture shows that the test set predictions are pretty reasonable, appear pretty reasonable, so that the assumption was, okay, we can try and make predictions with this QSA equation, with this QSA model for a larger database of sesquiterpene lactone structures which have never been tested against this parasite. This is just a small part of that table, of this database, in-house database of sesquiterpene lactones, which I have in my group or in my lab. And in the lower part of this graph, you see the predictions, the predicted PIC50 values for, also not for all of them, there were 1750 or 1750 sesquiterpene lactones in this table, and for each one the PIC50 was predicted using the descriptors, which were of course calculated, and then using the particular equation I showed you as a result of our QSA modeling. And each point here represents one compound and its PIC50 value here, and the ones shown in the red area are the ones with a predicted PIC50 of more than 7. That means an IC50 below 0.1 micromolar. Of the 1750 chosen sesquiterpene lactone structures, which are drug-like, which have drug-like properties in terms of Lipinski's rule of 5, by the way, 71 compounds were predicted to have a very strong activity with IC50 below 0.1 micromolar. So 71 compounds would be much less easy to obtain and to test than 1750. You will agree about that. And then one very major observation was in that case that 15 of these molecules belong to the so-called furanoheliangolide type, a particular class of sesquiterpene lactones with a basic skeleton looking like this. And I was lucky, with the help of some Brazilian colleagues, to obtain a few of these furanoheliangolide sesquiterpene lactones. And this slide shows you the predicted values with our QSAR model. And then, of course, we tested these molecules, and it shows you also the experimental IC50 value. And you can see that in all cases the IC50 values were quite low, and the molecules 70 and 71 here really had IC50 values below 0.1 micromolar, so they belong to the most active molecules we found so far. And then comes our nicest hit so far, which is not shown yet, but it shows up now. This compound here, also a furanoheliangolide, a little bit different structure, the double bond, the exocyclic double bond here. This is so far, and that is actually based upon the predictions with our QSAR model, the most active sesquiterpene lactone ever found in this series, with an IC50 of only 15 nanomolar. So, to summarize, this QSAR approach using molecules, not a single furanoheliangolide in the training set or the test set in our original data set, has led us the way to a new class of very highly active antitrypanosomal compounds with a different skeleton and even higher activity than the molecules we had found before. So we might have gone on for a very long time testing sesquiterpene lactone, so and so and so many, but this more rational approach has led us the way into a new class of compounds which we are now very intensively investigating for mechanism of action, etc., etc. Now, mining virtual compound libraries using such methods is a very straightforward way, with straightforward methodology. If you use MLR, you've now seen how it can work. The feature space may be much larger. We can have tables with hundreds and hundreds of columns, for instance, and we still want to analyze them, and then MLR may not be the proper methods. Because as a rule of thumb, as I told you before, or as I've also shown you, the number of X variables should not exceed 1/3 or better even 1/5 of the number of the objects. So what can we do in case of such larger data matrices? Let's look at our correlation metrics from the beginning, again from our capsaicin data. And as I already showed you, some of these variables are strongly correlated among each other. They are cross-correlated. The information in them actually is redundant. And in linear regression, we want as few dimensions as possible. So we might get the idea, okay, we can simply throw some of these variables out of our table, out of our data set. And doing that systematically, we would end up with a much smaller data set, with a much smaller set of variables. But if you look at this very closely, you will see that at least one of the more important variables in our data set was lost, because I go back here, our log p square is very strongly correlated with log p, which is in the table here. So it has a very high correlation coefficient with log p. So that is why, I'm sorry, I didn't use the arrow. So log p and log p square have a correlation coefficient of 1. So that means one of these variables would inevitably be thrown out of our table. But as we've seen before, the information of that variable is important. So the question is, can we reduce the feature dimensions or the dimensionality of our feature space and not lose any relevant information? There are methods to do that, or to achieve that. And the most important methods I will show you here. The first one is called Principal Component Analysis, PCA. And in that method, instead of eliminating redundant variables and maybe losing information, the common information content of the correlated variables can be combined in a set of new variables, so-called latent variables or principal components, which one by one contain one piece of information taken from these redundant variables, combining it, making one new latent variable, and thus reducing the necessary number of variables to describe the whole information content of such a matrix to much fewer variables. So PCA actually constructs a new feature space in which all dimensions, principal components, have a maximum variance or variance and are mutually uncorrelated. They do not correlate with each other. So the coordinate axes in that new feature space are the principal components, and they are all orthogonal to each other. They do not contain any piece of redundant information anymore. Depending on the amount of redundant information, a large part then of the variance in this in such a data matrix can be represented very often, at least, by much fewer latent variables than original variables were present in this data table. And still the distance, proximity, is correlated with similarity in this new feature space. PCA is used not only in the field of QSAR or in such chemometric context, but in many fields of chemistry, in many other sciences as well. So it's a very important statistical method to reduce the dimensionality of complex feature spaces. In case of QSAR or QSPR, models can now be made based on principal components, on these latent variables. We can generate models by correlating latent variables, and then we would not speak about principal component analysis anymore, but about principal component regression, PCR. Now what happens? Imagine you have two variables, redundant variables, or at least redundant for a major part of their information content because they have a high degree of correlation. Plot variable A versus variable B, two-dimensional feature space, and you see there's a huge or a big amount of correlation between them. They strongly correlate with each other, but eliminating one of them, you would lose completely the information which is hidden in the part that is not correlated between these two variables. You see that there is some non-correlated part, of course, in this information content, and that is simply this would simply be lost if you just eliminated one of these variables, just like eliminating the log p square value in our previous example would make you lose very important information. So what PCA does is actually it finds the maximum variance in these data and creates a new variable axis or a new coordinate axis, the principal component number one, along this maximum of information content, and a second one, in this case, orthogonal to the first one, which is related to the second or to the other part of the information which is not common to these two variables. So actually that means we have created two new coordinate axes. We have created a new latent feature space with two variables which are completely uncorrelated with each other. You see what happened here? So this is our new feature space, and we have two variables containing completely different parts of the information. The redundancy is gone. It's not there anymore. Now you may note that in this simple example we have not reduced the dimensionality of this feature space because it only consisted of two variables. But if you imagine you have a feature space consisting of 600 variables and many of them are correlated with each other, you will lose a lot, or you will reduce the dimensionality by many dimensions by simply combining the common information content into such latent variables. And that's exactly what happens in principal component analysis. Principal component analysis thus constructs the latent variables in such a way that each latent variable value is the sum of the original variable values multiplied by particular coefficient, the so-called loading or contribution of that particular variable to the new variable, to the latent variable. such a linear correlation of these original variables in the new latent variables then actually leads to principal components that explain the where the explained fraction of total variance in the data decreases. The first principal component has the largest explanatory fraction, or explains most of the variance in the complete data table. The second one is the one that explains the second most part of the or second largest part of the variance, and so on and so on. And usually the number of PCs needed at the end to explain almost 100% or to explain 100% of the total variance is much smaller than the number of original variables. And that can be of benefit, because you can reduce the dimensionality of such a feature space. Now, the typical output from such a principal component analysis is shown here. I've performed a PCA for our capsaicin data set, and you see here a plot of the first and second principal component generated out of the 12 variables. So we had originally 12 variables, a feature space with 12 dimensions. And what we can see in this picture is that the first two principal components actually explain 72% of the total variance in these 12 original variables. The first principal component explains 72%, and the second one and the first one together, the cumulative explanatory capacity is 86%. The first three PCs, the first three principal components, would explain even more than 90% of the total variance. So the question is, or it's not a question, of course it's evident that we don't have to bother with an 11-dimensional space if we can reduce the information content actually to 3 or maybe only 2 significant components. What is shown in the graphs is the first one is the so-called scores plot, showing you the positions of each object, each compound, each of the capsaicin derivatives in this latent variable space with respect to the first two principal components. And the loadings plot here shows you actually the contributions of each of the original variables to these two components, to these two latent variables. And what you can see is that the first principal component, we have here log P, for instance, on the left side, very far to the left, and log S, the solubility, calculated value for aqueous solubility, very far to the right side. So obviously the first principal component is related to the information content that has to do with lipophilicity. And the second principal component, you see that variable ASA minus and ASA plus have, and some others, ASA descriptors related to distribution of electrostatic charge on the molecular surface. They are mainly contributing to the variance on the second principal component. So these two components actually are the pieces of information that are most important to describe the variance in this data set. So far we have only seen the principal component that gives us an idea about the property distribution of within our data set. But there is a second method, or an even more important method when it comes to QSAR models, which is called partial least squares regression, PLS. And PLS basically does a very similar thing as principal component analysis, because it also constructs latent variables. But in this case, the latent variables are constructed in a little bit different way, because they are not only mutually uncorrelated and combine the major part of the information from redundant variables in one particular latent variable, but they are constructed in such a way that they have immediately an optimum or a maximum correlation with the target property, or they explain as much as possible variance in the Y data, in the biological activity data for the QSAR example. And that means that these latent variables, or PLS components, which are then generated, they are mutually orthogonal as in PCA, but they are all maximally correlated with our target data. So that is actually the method we use most widely for QSAR purposes, because the output of a typical PLS modeling would look like this. We get a very similar output, a scores plot showing us the position of each object in the latent variable space, the PLS component space. Each compound has a particular position here. In this case, we can, of course, color them by activity, for instance, and we see, of course, a very active compound is shown here on the right side, and we get in our loadings plot also an explanation for the variables that are actually responsible for the position of a particular compound in a particular part of this feature space here. And we see all the variables clustering here around our log P value, which is somewhere here, are related to hydrophobicity or lipophilicity. So that shows us again the same result as we had before, that lipophilicity is the most important factor in this data set for activity. And then we also see that our second or our other piece of information, this ASA plus variable we've seen before, it is most strongly influencing the activity here on the second latent variable, on the second PLS component. So this way we have not thrown away any information. Log P and log P square are still in the model. We obtain a very nice fit of our data, calculated versus experimental versus calculated activity data, very good linear fit. We have not lost any information in our data table and come to a very similar result as we have done with multiple linear regression previously. In this case, it doesn't make a big difference which method you use. But as I said, it can make a difference in cases where, sorry, let me go to the next point here, in cases where you are using or where are dealing with huge data tables, like in so-called 3D quantitative structure activity relationship, 3D QSAR studies. I will not have the time to go into detail about 3D QSAR in this webinar. Maybe I can do this at a later point, but you can simply imagine that we align the molecules we want to study in a virtual piece of space, actually. We align them according to a joint or a common binding hypothesis. We need a receptor binding hypothesis for these molecules, a common orientation in the receptor. And then we calculate for many thousand points in this virtual cube here, representing different positions in a very fine grid. Actually, we calculate the interaction energies of each molecule with a particular probe atom, which we put in each of these positions. So for each of these positions, for each probe atom, we will get a descriptor, and that can result in a huge data table. So if you say this is a cube with 10 angstrom length on each side, and we define the cube, the grid points in distances of 0.1 angstrom, you can calculate how many million different data points we will get, and each of these data points representing a particular interaction energy at a particular point with a particular probe will be represented in the table as one column. And so you will have a huge column, and usually in this case PLS is used, partial least squares regression is used to filter out those variables that have the most influential or the highest influence on the biological activity of the data set that we look at. And then of course the coefficients can be color-coded, they can be mapped back around the molecules, and the regions that you see in the right graphic here represented by different colors simply show you regions which are very influential for receptor binding of this set of molecules. But as I said, 3D QSAR is not something we can go into detail at this point in time, but what we can do is, or what we should do in the remaining time, to look at an example or at the possibility to mine physical natural product libraries. We've seen a little bit about the statistics and the modeling methods that can be used for QSAR models. And as I said in the beginning, we can use relatively simple uh, multivariate statistic methods, similar methods as for QSAR, to analyze the information content of such extract libraries, for instance. So mixtures of natural products, whole organism, extract fractions, etc. They can be treated as libraries, of course, and analytical data we obtain from them can provide information about the constituents. And these can be treated like the features in our QSAR examples. Multivariate statistical methods can then be applied to such data in a very similar way as explained before. Now, the analytical data used most widely in this respect are NMR spectral data, mostly proton NMR data, can also do something with carbon-13 data, but usually proton data are used as values put into an X matrix, as I will show you a little bit later. And then, of course, chromatographic data, usually obtained by hyphenated techniques like GCMS or LCMS. And then, of course, we can apply data analysis methods to such analytical data to elucidate relationships between the samples in terms of similarity, dissimilarity, which features, which peaks, for instance, or which NMR signals are responsible for similarities between, or most significantly responsible for similarities between our samples. And of course, you can imagine we can use principal component analysis for such studies. We can also use methods of cluster analysis or other unsupervised methods, as we say, but to identify constituents of relevance to a target property like biological activity, for instance, we can once more use partial least squares regression, because in this case we will have a huge X matrix with many descriptors or feature values to correlate with a particular biological activity value. And then we have the possibility to use partial least squares and something called partial least squares discriminant analysis. So these are the major methods, or some major methods that can be applied to such data. Now, how do you have to proceed? I will show you this in an example from a recent doctoral thesis here by Dr. Therese Ellendorf, who obtained her doctoral degree in my group together with Dr. Jan-Dirk Sendker from our institute, who also was a co-mentor of Dr. Ellendorf. And what we did in this study was to study to investigate the anti-Trypanosoma brucei activity of walnut trees, of walnut species. Different species of walnut and different plant parts of these trees were extracted with different solvents, actually. So we had an assembly of 36 different extracts, and all of them were tested for growth inhibition inhibitory activity against Trypanosoma brucei, the parasite I talked about earlier, at a concentration of 10 micrograms per mil. And this table, you are not supposed to read this table, but you can see that it contains the antiparasitic or percent growth inhibition data against TB, among other parasites, which were also tested. And of course, that is a set of extracts. All of these samples, that is just the second part here of these data, all of these samples were analyzed by UHPLC, ESI, QTOF, mass spectrometry, and MSMS. So what we obtained was, of course, this is only a small part of the samples that were investigated, was an assembly of chromatograms containing information about retention times of the constituents, and of course, for each constituent, mass spectral information. So at each point here, or in each interval, in each time interval of these aligned chromatograms here, we could extract, of course, the mass spectrum. And from these mass spectrum retention time informations, we generate variables or feature variables, descriptor variables, if you want to call them that, containing information about the M/Z values in this particular mass spectrum at a particular retention time. So we obtained many variables of that kind, from the aligned base peak chromatograms of these 36 walnut extract samples. And then, of course, we combined them in a data table, a large data table consisting of about 400 such variables. Of course, we did some pre-filtering, and variables with too little variance were discarded in the beginning, but those variables that appeared useful for such a study were about 436 samples, of course, and the values in this table for each particular MZ time pair, the peak area or the peak size actually is the value that you put in this table. Of course, our target data, our dependent variable, was the percent growth inhibition of T-Brucey at 10 micrograms per milliliter. And then we submitted this data table to PLS, this time using a little bit different software. So the picture looks a little bit different from the one I showed you before, but it doesn't make a big difference. We have a scores plot again on the left upper quadrant here. We have a loadings plot or loading weights plot here, showing us the influence of each variable on the particular position of our samples in this scores plot. You see that the samples with high or with shown in red are those that are close to 100% growth inhibition. So these are the most active ones. And the variables clustering in the same part here of the loadings plot, they are shown with little circles. These variables were found to be influential for the high activity or correlated with the high activity of the highly active samples. So the result of this PLS regression is shown here. This is a coefficients plot showing us the correlation coefficients of these variables, which also have a strong positive correlation with activity. And this is a predicted versus experimental activity plot where we have the predicted values from this PLS model plotted against the experimental activity data. And the fit is also quite good. So what is behind this, or what does that mean actually, or what information can we take out of it? We can, of course, go back to our mass spectra and search for these variables here, or look at these variables and assign them to particular retention time mass spectral information pairs. And that means we can find these variables in our chromatograms and, of course, assign them to particular compounds. And in this case, it was really an interesting finding that here is a list of these variables, these influential variables most strongly influencing the PLS correlation, that actually all of these variables, with only very few exceptions, but all the variables shown here in this table correspond to the mass spectrum or are representing the mass spectrum of one particular compound. This mass spectrum is shown here. And you can find all the fragments or all the MZ values, the mass signals shown in the table, which are apparently important for bioactivity. You can find all of them in one particular mass spectrum. So that means probably one particular compound in this case is really important for the differences in activity between these walnut samples. If this compound is present in a high concentration, activity is high. If it's there only in a small concentration, activity is low. So that is something we can already expect at this moment. The mass spectrum is here, the AZ mass spectrum, and of course it is then straightforward to go back to the extract to further characterize this compound, look at the UV spectrum online, then of course to isolate this compound, to record the NMR spectra, and then to identify this compound. In this case, we ended up with this compound here, which is a known compound, known to occur in walnut species, but it had not previously been reported to be responsible for antitrypanosomal activity of walnut samples. So the targeted isolation of the most relevant compound, most relevant for anti-TB activity detected in these samples, led to the identification of hydroxyglone 4O-beta glucoside, very simple naphthoquinone or naphthahydroquinone glucoside. And of course, you can then test this compound again. That's what we did as a pure compound against the trypanosomes, and end up with a not really impressive, but still quite active or kind of active IC50 value. So the hydrojuglone glucoside is really the most active compound we could find in this walnut, in this group of walnut trees. And of course you get a source for new ideas, but in this case, for instance, to test other naphthoquinones. In this case, the quinone forms, the juglone here is actually the naphthoquinone you get if you cleave off the sugar here and oxidize the whole thing to a quinone. And we found that juglone, the corresponding naphthoquinone, is already a big deal more active than the glucoside here. But at the same time, it is also more toxic. We also determined the selectivity index. That's what we always do in comparison with a mammalian cell line. Growth inhibitory activity is shown here. And you can see that juglone has a lower selectivity index than the hydrojuglone glucoside. So the native compound is actually less active, but it is also much less toxic, which could give you the idea to maybe produce glucosides from other naphthoquinones, which we've tested and which have been shown to be even much more active than juglone itself. So this leads also not only to new molecules, but also to quite interesting new ideas what can be tested in the future. And if you are interested in this method or in these methods in more depth or in more detail, I would also recommend that you take a look at the recent PhD thesis of my student Mauro Nogueira, a Brazilian student who recently graduated in my group and who has spent his whole time and all his work on investigating chemometric and chemoinformatic tools to identify targeted isolation of compounds from particular plants using such multivariate methods here. So at the end of this webinar, I just want to draw your attention again to one particular fact, something which is actually more or less self-evident, but something that cannot be stressed often enough. Linear regression can help us to transform data into knowledge, as you've seen in the few examples I showed you, to interpret data and to get knowledge, but it does never, or it probably never gives all answers to any question you may ask. And especially extrapolation of a linear model can be very tricky, because a linear model can only reflect the information you've put in the model. And extrapolation, at least in strong cases, or to extrapolate to something completely different, may be, of course, impossible. Like, for instance, in this example, imagine your wife tells you every day she loves you more. Then love will increase linear with time. Love is plotted versus time here, and you will get a very good linear correlation. But if you extrapolate that, it would actually mean that before she met you, she must have hated you, which is, of course, completely wrong conclusion from this linear correlation. Okay, so a little joke at the end. Please keep in mind, linear models can do very important things or can give you very important information, but you should always treat them with due care and not extrapolate them to regions of probability that are not really covered by them. Finally, I have a slide here with some books, recommended reading, Handbook of Chemoinformatics, for instance, edited by Johann Gasteiger, very famous chemometrician, and some other books here. I don't mention them all by names. These are books mainly if you're interested in quantitative structure-activity relationships. In case of the other methods, investigating extracts and finding active compounds by multivariate statistics, I would refer maybe to metabolomics textbooks or books on metabolomics. There's, to my knowledge, not a particular book yet on this particular part of the field, but it will probably, because it's an emerging field, not take too long until something will emerge in this field. So this is actually the end of the webinar that I was preparing for today, that I prepared for today. It took a little bit longer than maybe usually the webinars may take. I hope you found it a little bit informative. I must say that for me it was a pleasure, even if I was speaking for 1.5 hours in front of a camera and not in front of an audience. And in case you have any questions, please feel free to contact me by email or any way you would like to. I will be happy to answer your questions, and maybe one day we meet again personally at one of the GA conferences or wherever. Thank you very much for your attention, and see you once more again in the future.